All right, so this is Lecture 2, CSC 227, Summer 2021. We're talking networks here. This is probably going to be the most technical of all the lectures we do this semester. This class isn't intended to be like a technical deep dive, like an engineering class, but because understanding very, very basic elements of how networking works is so important, when we start building on top of other concepts, that we dedicate a lecture to it. Now, I'm going to be covering a bunch of different things, which is fine. I will point out things that really are nice to know, and then I'll point out things that you need to know and need to remember, because they will come up throughout the semester. Okay, so let's get into it. If you do not have a background in technology or computer science or anything like that, that's fine. That's fine. This is intended to be accessible to everybody. So I will do my best to be very clear and very inclusive. If you have any follow-up concerns, reach out to me. Understanding networking is going to be important as we move through this semester, okay? All right, so in this lecture, I'm going to describe the OSI model. This is probably one of the top two things that you need to take out of this lecture. There'll be a graphic with the OSI model on it. We'll talk about it. There's a couple layers in it that are critically important, and I will explain them so it resonates with you. I'll make it practical, all right? We'll talk about the use of MAC addresses, which is kind of a unique identifier for network interfaces on computers. We'll talk about major protocols, obviously. That'll all be hooked into the OSI model. We'll talk about connection speeds and methods and kind of cabling and hardware and stuff. That's less important. It's not really relevant from a cybersecurity perspective, but it is networking concepts. And we'll talk a little bit about networking devices like hub switches and routers and just give you a brief overview on what those are. So as far as, understanding how data is transmitted, that second bullet, that's really what the crux of networking is. Networking is essentially two computers communicating and exchanging information with each other. It's literally how the internet works. Now, my computer isn't attached to your computer, yet you're somehow getting this information, right? The reason is because my computer connected to YouTube and pushed the data up. Now, YouTube server isn't in my house, literally connected to my workstation, right? It's somewhere on the internet, and there's a collection of routers and switches between my computer and YouTube that the network traffic, the data of this video file, traversed across the internet until it got to where it was going at YouTube. Same for you watching this video. You went to YouTube, and YouTube is connecting to you across multiple hops and pushing this data to you, right? So this is what's going on under the hood when it comes to the way the internet works and networking in general. We'll get our hands dirty a little bit so the lesson applies. So for cabling, if you can't read this, the slides are available for each of the lectures, but essentially this is the different categories of cabling. Don't spend a lot of time on this. I will point out Cat 5. We call it Cat in the industry, not category, but Cat 5 is like the most common one. This is what you see it like in your home. If you've ever seen kind of like the blue cable connected, you plug in your home computer or whatever, that's Cat 5 cabling. Obviously you get faster speeds at, at businesses and stuff like that. But this is the cabling. You don't really need to know too much about it, okay? Other connections. So again, the cables you use to connect is one thing, though the speed at which internet service or networking capability is delivered to your home, for example, is by an internet service provider like Comcast, right? Or Frontier or Spirit or whatever you want to use here, Verizon. Well, they can make basically the gauge of the straw bigger, right? For more money. They'll give you a pipe this big if you want. So the bigger the pipe, the bigger the data flows, right? Now you'll see that OC came in and it's doing 155 at its base layer, OC3. This is, we're getting into fiber optics at this point, which is pretty standard. If you live in a neighborhood that offers Fios or fiber optic internet, you know it's fast, right? So you can just see as they start stacking fiber optics together, the bandwidth goes through. So more bandwidth, the better, right? Especially in today's day and age where everything is online. You can't stream Netflix at 1.54 megabytes with a T1, right? Wi-Fi. So this is all physical cabling, right? Wireless, which many of us now use as like just standard practice, has evolved over the years. Now the standard that defines the protocols is across the top, but 802.11 is basically wireless, and then the letter at the end indicates kind of the iterations of that. What I want you to really take out of this particular slide is just the idea that as time has passed, the speed has increased significantly, right? So don't worry about the frequency with which it's at. 5 gigahertz is faster, right? But you could see it was 54, then went down to 11. That's not good. Back up to 54 at the 2.4, then 600, then 1.3, now 10, 12 gig. So if you can get a home router with 802.11ax and your workstation has an 802.11ax compatible network interface card so it can speak in that protocol, you have blazing fast speed on your wireless network. So just the key takeaway here is everybody's using wireless, and thankfully the people who are working on wireless technologies continue to make it incredibly fast. So here's a little bit of history on the different protocols. Essentially, these bullets are going to just say what I just said. You can see that it was widely used because wireless is awesome, but it was slow. Over time, they started making it faster. With 802.11n, they started actually including like security type stuff, because originally like 802.11b and G were like that. It was always about the speed, right? Let's make it faster, make it faster. Well, the security protocols of like actually encrypting the network traffic and making authenticating to the access point, like jumping on the wireless network. The security wasn't really great with that. So in future iterations, they actually increase the level of security, which is awesome. And we'll look a little bit closer at some of that stuff later on in the semester. Okay, so just as time passes, it gets faster, it gets better. That's all you need to know. I wouldn't spend too much time on that. What we should spend time on is the OSI model, because this is the most important thing of this lecture, okay? And there's a graphic right here that we'll look at. But OSI is a 7-layer model, right? It's a network model, okay? Now, this is how it works, okay? When I type in google.com in a web browser and hit enter, or I search cybersecurity on Google and hit enter, the screen goes white for a second and then my results pop up, right? Like everybody uses the internet. Everybody has Googled at some point. Like that's how it works. You put in your query and the responses come up. What is happening is you're putting in the query on your local workstation. When you hit enter, it takes the data, puts it into packets, and then puts the packets on the wire, which means it's the physical layer of it going out, and it transmits it out. And it is sending several, like just type it in cybersecurity in Google and hitting enter. It's still sending thousands of packets, right? Across frames. This is how it works. So then it sends the packets, and then when it gets to its destination, it reassembles it, and then the server at Google does something with the data in it and then sends a response back. Okay, so let's go a little bit deeper on this. Okay, so the green layers, I don't want you to spend too much time on because they're not as important, but think of this as like the web browser, right? The application is your Chrome browser. So you're typing in google.com or cybersecurity in the Google query in the web browser, and then you're hitting return. The browser is built to understand this network stack and parse your data in a way that it can be sent complying with network protocols to Google. All right. So here's where we are, our adventure begins, or here's where you really need to start, taking notes or wrapping your head around this. The transport layer is the first layer with where services and ports are. So if you've ever heard of ports or services, this is the layer that this is at. This is more important when like on the receiving end, because you have listening protocols. But with the transport layer, things like TCP, Transport Control Protocol, and UDP, which is User Datagram Protocol. You don't need to remember what the acronyms mean, just TCP and UDP. We will see TCP a lot this semester, okay? This is how the connection at the end is built. Now, UDP, just to spend a second on it, UDP is connectionless and doesn't care if your packets get to where they're going. It literally just sprays. So if you've ever watched streaming media and your network bandwidth is low or something like that, and it starts getting pixelated, the reason it's getting pixelated is because the data isn't all coming across the wire because of whatever problems you're having. But the thing is, UDP isn't going to resend the packets. It's literally just firing the packets off. And so that's why you get pixelation, because there's missing data there and it can't make the picture crisp. Okay, so that's what UDP is, an example of how you understand it. Let's spend some time talking about TCP, because TCP is really the workhorse of the internet. TCP, TCP has a thing called the three-way handshake, the Transport Control Protocol three-way handshake. And effectively what it does is, before, like I said, you hit enter and it sends data to Google. Before any data gets sent, what initially happens is your endpoint or your computer or whatever sets up, it does a handshake with the receiving server in order to ensure that all the data you're about to send successfully gets sent and received by the server. So with this three-way handshake, it's called the SYN. Here, maybe I can find a quick little example, or not example, but visual. All right, so just to illustrate this point, this is what the three-way handshake is. In this example, this is our workstation and this is Google, the story I've been telling so far. Okay, before any data is sent, our computer sends out a single packet with the SYN flag marked on it, right? So you don't need to know flags and stuff like that, but just know that it says it sends a SYN packet, right? If the server receives it, it sends back a SYN ACK packet saying it's acknowledging the sync packet, right? That's what SYN means, sync. So then once our computer gets the SYN ACK packet, it says, okay, the server's there. The server knows that I'm trying to communicate with it. Let me send the ACK packet back to them. Once that is done, the connection is established and now data can start being sent across. The reason that you need to do this is because of the following. Once you start sending data, the packets when you're doing TCP, the packets will get numbered, right? So packet 1, packet 2, packet 3, packet 4, packet 5. When the server gets it, it receives packet 1, packet 2, packet 4, packet 5. Packet 3 didn't come. The server will wait a period of time and then it will send a message back to the host saying, I did not get packet 3, resend it. So that is ensuring that all of the data gets sent to the server. Additionally, because of whatever routes it's going to travel, because there's many ways for the route or the network to go from here to there, the server could get packet 1, packet 2, packet 4, packet 3, packet 7, packet 5, right? They're out of order. The server doesn't take it and start stacking them on top of each other as they come in. It literally builds a buffer, and it has, like I'm expecting 30 packets, right? So it has, packet 1, packet 2, packet 3. And as the packets come in, it starts stacking it and assembling them in the correct order that it should be receiving it. So then it'll actually, it'll know also they're in the right order, but also where the gaps are, and it can ask for that resend. This is the power of TCP. Now, why wouldn't we use TCP for everything? Because there is this additional overhead in maintenance. There's a performance hit, which we don't see very much anymore. But if you are pushing like 4K video streaming, this is why video streaming is great in UDP. If you're pushing 4K UDP and you introduce this overhead, you lose quality and fidelity of the stream. And in reality, do you really care if the scene that you're watching, the show, has already passed? Then data from a previous image on the screen is no longer relevant. It would get dropped by the server anyway. So that's why you wouldn't use TCP in all instances. But for the most part, TCP is the workhorse of the internet. When you connect to basically any web server or anything like that, mail, it's always TCP, and we'll see some of that later on in the semester. Okay, so this, by the way, we're still just at the transport layer. We're just at the transport layer. Okay, so but hopefully you get that. It's TCP, and that's kind of the handshake. Also at the transport layer, what we talk about is listening services. So when you have a server like Google, right? Google is waiting. When you type in google.com and hit enter on your computer and it establishes that connection, the server is listening on a known port, right? This guy right here is listening on port 443. The ports are numbered. They go from 1 to 65,536, okay? And certain ports have certain meaning and certain, they're almost like keywords, like they're already predefined. And port 443 is encrypted network traffic port. So all servers are listening on port 443, web servers. And once you establish a connection, they'll bump it up to some high-level port, and that's where the data communication will go. But port 443 is where it's listening. And again, that is at the transport layer, okay? So hopefully this is beginning to resonate why understanding OSI model is so important to like everything else. Okay, again, don't get overwhelmed by this, all right? This is definitely the most technical of the lectures that we're going to do this semester, but it's just so important, okay? So going down the stack to the network layer. The network layer is where IP address scheming happens. So if you've ever heard of like, what's your IP address, or give me the IP address on the back of the phone or on the back of your computer, that is your network layer address. And IP addresses are unique on a network, right? So you can have multiple services running on one machine, but only one IP address per, well, you can have multiple IP addresses per machine, but you can't have two machines on the same network with the same IP address. So for your home network, your TV, your Google Home, your phone, if you got it on wireless, you have guests come over, they hop on your wireless, they all have unique IPs from each other. Some of you may have actually experienced a situation where you ran out of IPs and it didn't make any sense because you had more than 255 things on your network. It doesn't happen often, but so IP address scheming is where this happens, okay? And it's important because going back to this example here of this server, when you're sending the SYN packet out, at the transport layer, before you did that, you actually had to know where this server sits on the internet, and it sits with an IP address. Now, real quick, as a quick aside before we go deeper into IP addressing, I want to point out something very specific or special called DNS. DNS stands for Domain Name Service. And the easiest way to remember it is because we use it all the time. DNS is the protocol that takes the domain names that you and I know all the time, like, oh, go to Instagram.com, go to Facebook.com, right? Like, that's how humans talk to each other about resources on the internet. How do I get there? Oh, type in Netflix.com and hit enter. Okay? Computers don't care about that. Computers care about IP addresses. So DNS is the service that translates domain names like Facebook.com or Amazon.com into IP addresses, which we'll look at in a second. And that's how the internet works. So if you ever type in Google.com, literally the first thing it does is try to do DNS to translate what the IP is, and then it starts trying to do the handshake and all that stuff. Okay, so just to give you an example of what IP addressing is, so we understand what we're actually talking about and looking at. This is my computer that I'm recording this video on. This is a terminal shell. You don't need to know that. We're going to learn it in the labs. And I've asked the terminal to show me what my IP address is. Now, there's a lot of noise here, so don't worry about it. But right here is my IP address on my home network for this computer. It's unique, right? 192.168.1.144. This is a valid IPv4 version 4 address. it's always 4 octets, meaning 4, a number, dot, a number, dot, a number, dot, a number. So there's 4 of them. It's called 4 octets, which is, by the way, why it's called IPv4. Now, what I want to tell you is 2 things. One, the number in each octet will always be between 0 and 255. It can never be above 255. And I could get into why. It has to do with binary and it's 8 bits and all this other stuff. But that's important to know. Secondly, and also worth noting, is because there's only 4 billion IP addresses, if you do 0000, 0001, all the way up to 255, 255, 255, 255, there's only, like, it's over 4 billion, but it's like 4,100,000,000 or something like that. There's a finite number of permutations that you can do. And as I just mentioned, these addresses have to be unique. So how do we continue to operate if we ran out of IP addresses a while ago? So what do? The protocols on the internet gods, right? The way that protocols are written and stuff have allocated special network segments for non-routable, meaning you cannot go on the internet and have these routables. 192.168.0.0 basically 192.168. Whatever is non-routable. So you'll see a ton of people home networks with this first 2 octets, right? And it's because it's a private network space on my home network. There's 2 other ones. There's 172.16.0.0 through 172.32.255.255. That is a private segment. It's bigger than the 192.168 space. And then there's another one that is, the first octet is 10.0.0.0, and that's the largest non-routable private IP space. And typically that's for like large organizations that are going to have, hundreds of thousands of endpoints. Think of like, Amazon or IBM or, Microsoft, one of these juggernauts, right? There's also another special IP address, 127.0.0.1. This is a unique IP address, and it's special because it is the local host of the computer, which means if things are broken, like say I can't get an IP address because the IP address has to be issued by the router of the network, and we'll talk about routers in a minute. So that's where the IP address comes from. It's not like my computer just makes up an IP address and hopes that there isn't a conflict with another computer on the network. It asks for an IP and then it's dynamically granted one by the router. However, every system has 127.0.0.1 because it allows you to troubleshoot and hit that IP address and determine where issues are. So that's called the localhost IP address. And then, obviously this is my IP address. Okay, so we will look at all sorts of different IPs today. Like just to give you another example, right? So Nslookup, don't worry about this. You don't need to do this. But like I told you earlier that google.com is how we remember things, but google.com is an IP address. Nslookup is basically allowing me to do the DNS function. This right here is Google's IP address, right? You see, it's still 4 octets. It's still between 0 and 255. And, that's it. Here's another IP address. This is actually my DNS resolution service. Again, don't worry about that. But you can see it's 4 octets between 0 and 255. So, all right. Hopefully that's crystal clear. But as things traverse around the network, this is the stack that they're using, right? Okay. So now we've got our transport layer. We got our unique identifier network. IP address scheming. Go one layer lower and we've got our data link layer. This is where MAC addresses sit, and this is either a wireless card will have a burned in assigned MAC address, or like when you plug in an RJ45, like an Ethernet cable into a Ethernet cable slot on a computer, that is that Ethernet cable is plugging into a network interface card, which has a MAC address on it, right? So MAC addresses are 6 octets. They're 2 hexadecimal numbers let me show you. It's probably easier to show you than it is to describe it. All right, so check this out. This is, again, my computer, and you can see it's still the same IP address, right? But the MAC address is also here. It's right here. It says Ether, but don't sweat it. This is the MAC address. This is 6 octets, effectively, and it's 2 hexadecimal numbers. Hexadecimal is a way of counting, like we count normally 0 to 10, right? So base 10. Hexadecimal is base 16. It gets a little confusing. You don't need to fully understand it. Just know that it goes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, right? And then it starts over and says, you know, it's 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, blah, 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 1, F, right? So you can see these are mostly numbers, but there is an F right here, which is how we explain that. So this is the MAC address. This is the unique identifier for the wireless network interface on my computer, okay? And the really interesting thing is these first 3 octets, because this is burned into this device, the first 3 octets actually typically identify the vendor of the device. So look at this. I put in the first 3 into this, you know, URL hardware address lookup, right? And all 1498.77, all of them from 00000 to FFFFF, Apple Inc., right? And I'm on a Mac Pro here. So that's another interesting thing about MAC addresses, okay? And then once we get below the MAC address layer, this is the physical layer, and this is basically what you would think. This is where data and energy is pulsing out of your computer, right? It's either light flickering on fiber, it's wireless network traffic communicating over radio, or it's on the wire for Ethernet. This is where that is. So, I mean, if you've ever had like troubleshooting and something wasn't plugged in, that is a problem at the physical layer, right? So this is the OSI stack. Let's spend some more time going through the rest of the slides and talking about it, but this is absolutely really important. And I would argue that like the transport and network layer are really the 2 layers that you need to really focus on the most. If you're gonna try to, if I know some of this is confusing, but like these are the 2 layers. And again, I'm not gonna like test you on like, you know, subnetting a network range or any of this other stuff. I'm introducing you to the concept. So when we start talking about malware and you know, techniques used by hackers, it'll make sense when they're attacking a specific service at the transport layer. That's the point of introducing all this, okay? Let's keep moving on. So a network is 2 or more connected computers, right? You don't need a router or any network device in between. You can connect devices, but for the most part, like 98% of the time, they are connected through network devices. Like all the machines on your home network might be connected to a wireless access point, right? Like a wireless router. Again, they all use NICs, network interface cards. This is where the MAC address resides. And it says it operates on the physical layer. It actually operates with the physical layer. You see the physical addressing here, but it's not at the physical layer. Again, RJ45 or wireless, pretty standard, right? The MAC address, I've already explained. This is the hardware that allows the data coming in from above the stack to get pushed out and transmitted in a way that makes sense at the physical layer. Okay. I did mention DNS. I showed you an example of DNS. This is the deal. It basically translates domain names into IPs, IPv4 IPs, okay? Again, you'll notice the 4 octets, and it's, you know, between 0 and 255, okay? This is more on cabling. We don't really need to spend any time on it. Just understand that there's different type of cabling for different, you know, reasons. And they can only go a certain distance, right? So a lot of people don't know that, but you can't have like a cable that's like 50 miles long that isn't set up to handle that type of length. Like basically, the energy carrying the data will dissipate and stop and not be able to travel that distance, right? So you need to put in relays that'll boost the signal as it travels over distances and stuff like that. That's how we're able to like communicate with Europe and stuff. It's not magic. This is, if you haven't seen this before, this is what an Ethernet cable looks like. It kind of looks like a telephone cable. If you still remember what telephone cables look like, those are kind of deprecated. But yeah, this is it. Most people use wireless though. Okay. Now let's talk about some networking devices, right? So we've kind of talked about the endpoint, or your own computer, and how it works up and down the network stack. But when you're sending data out, it needs to go over a network through networking devices. And that's the three things that we're going to talk about right now. So there's hubs, switches, and routers. Hubs and switches are very similar, except switches can take in data from one point, one computer or whatever, and send it out to another computer, whereas a hub will take it in and send it to everybody on the network. Do I have a picture here? Yeah. Okay, so this is a server, this is your computer, whatever. This is a router. A router connects networks together. Router is routing traffic, and a router is like how traffic traverses across the internet. So just to have an example here, again, look at 10.0.0. So this is a non-public routable IP address space. This, however, is public routable, which is, this is a bad example. This shouldn't be here. But so if this server wants to communicate with PC2, or PC2 wants to communicate with this server, right? This PC sends the message out to the switch. Switch is routing at the MAC address layer, okay? At the MAC address, at the data link layer. And this thing says, I'm trying to send data to this server. Is the server connected to the switch? Does the switch have that server anywhere on it? Switch says no. It says, all right, well then send it on to the router, and it's going to go by way of this server, right? So it gets sent up and goes through, hey router, do you know where this server is? Is it on any of the networks you know about? Yeah, it is. All right, send it here. Then the traffic comes back down. When it's coming into here, into this switch, the switch knows what the PC is, and the data is mapped in such a way to say this is where it's going, so it'll send it to PC2. Now, the hub, using the same example, the hub PC2 says, okay, hey, I'm looking for this server. Okay, I don't know where it is, but when it comes up here, literally the request goes out to PC1, PC4, PC3, PC5, and the server. So it's very noisy. The hub is basically a dumb switch. A switch does everything a hub does, except it doesn't send it out to everything. The hub kind of does everything the switch does, but instead of having the logic of like, what is it seeing and keeping a kind of a table of it, it sends it to everything, which, in case, you probably already figured out, this can be really noisy and result in like a denial of service attack on the network, right? So that's the difference between that. And then the router is special in that it can connect these two networks. So if you have a router at your house, you're connecting your home network to your ISP network. That's what's going on there, okay? And typically the router is where you're going to get your IP address. When you plug a computer into your home network and it gets an IP address, it's typically the router that is sending that. The router keeps track of all the IP addresses of all the devices on the network. That's part of its job. That's how it knows where to route stuff. Let's see what the slides say. Right, so the slides, this is a hub. It's a layer 1 device, meaning the physical layer. There's no intelligence of the hub to understand the MAC address and stuff. It's literally just taking the signal and bursting it out all the other ports that are connected to it, right? A switch, on the other hand, is a smart hub. It sends packets only to the intended host at the layer 2, right? So going back to our OSI model, layer 2, right? The layer 1, 2, 3, 4. Layer 2, with the MAC address, because the MAC address is a unique NIC. If it knows where that unique NIC is, it knows where to send it, so you have less traffic and less noise on the network. And then the router is sophisticated, right? It limits traffic to an intended network, right? Pretty straightforward. Continuing on about internet connections, we had a slide a little while ago about different types of cabling, right? T1 and T3 were kind of fast. OC, optical connection, fiber optics was much faster, right? That's what this is saying. Don't sweat this too much. This isn't super important, this part right here. So I've kind of talked about how data is transmitted, like when you hit enter after you type in your query into a search engine and it goes across. This is basically what that's saying. It sends packets, and we can watch traffic on a wire using a tool to watch packets go through. Okay, packet is divided into a header and a body. The header is how think of the header as like the outside of the envelope and the addressing and everything, where the body is the letter inside the envelope. That's essentially what it's doing, and it's really very similar to mailing mail with the envelope and then the data inside the envelope or the message inside the envelope. Okay, and that's how it works. We don't need to go too much deeper into this. Okay, this is basically saying what I just said. Okay. Protocols, right? They kind of control, like everybody agrees to certain protocols. That way when you implement things, you know it'll work with other people's networks. You don't have to coordinate with them. You don't have to have special rules. Like everybody just agrees that these are the rules that we're going to use. And that's why we can have 802.11 wicked fast wireless networks and stuff, because vendors are making products that use the same protocols that the networking device companies are using to communicate with those devices. So protocols are good. Again, you don't need to sweat them, just know about them. Okay? We talked about TCP, we talked about IP, definitely the most important protocols of the modern internet. UDP I spoke about already, and ICMP, there's different things for ICMP, but what most people think of when they think of ICMP is ping. We will, I think we do a lab actually with ping, but just to kind of give you an example, ping is a network troubleshooting protocol that basically allows you to detect if a host is up. Remember that client server model we looked at earlier, and it did the three-way handshake? Well, ping is a UDP thing, right? And it can like basically see if something's up. So this was my DNS resolver earlier. Let's ping it and see if it's up. See how the messages are coming back? Right? So 5 packets sent, 5 packets received. It's pinging and coming back, pinging and coming back. So now I'm just going to make up another one, right? And just, this is whatever, a routable IP address on the internet. I don't know where this is or what this is. But you see, that IP address that I just made up, there is no server on the internet currently with that IP address, okay? It could be turned off. It could not be assigned. It could have a firewall rule preventing ping from working, but for the sake of this point of the discussion, that's the point of ping and another actual kind of use case of the protocols, right? All right. So a port is like a listening service. Think of it as like something that's waiting to receive something, right? Like think of it a relay race where the person who's about to receive the baton has got their hand behind them and open. That is essentially like a port, right? And the person running up handing them the baton is the client wanting to connect with them. Okay, it's not exactly apples to apples, because once you hand them the baton, you are also not going to let go because you want that connection. But anyways, yeah, it's not a physical port. It's not a hole in the computer that you stick stuff in. It's literally a software construct to allow systems to communicate and interface with each other. Bluetooth is another protocol that we don't talk much about, but yeah, I'm sure you use it, right? If you got AirPods or if you got home digital assistant devices. Again, the key thing to take away here is over time and over iterations, it gets better. We've got faster bandwidth. We've got longer distances that we can cover. It's great, especially Bluetooth, because it makes life convenient, right? ANT Plus and NFC, these are just some other kind of wireless protocols. ANT Plus, you don't really hear about. NFC, you do see some, like some of these phone chargers, like the Samsung phone that you can put down and it'll start charging. If you've used swipe badges to swipe in or key fob to unlock a garage or something like that, that's NFC, right? And you're transmitting data, right? That's what's going on. Zigbee, just another one. Like really, you can read the slide, but the whole point of this is to emphasize that it's not just home wireless networks. Like we are pushing data using all sorts of different wireless protocols for different applications and purposes. So it's very cool, right? But it's all data. It's all traveling between endpoints, right? So the internet, right? We're all familiar with the internet because it's awesome. The internet is, that blocks of IPs that are owned by internet service providers. Each kind of region in the world has a bucket of them, and then there's an organization that kind of handles doling them out-ish, and then private businesses like Verizon, Comcast, etc. purchase bundles of them, and then they're responsible for doling them out to individuals, right? So your home network has an IP address on the internet that's basically allocated to you by whoever you pay your monthly bill for, right? That's what's going on there. Okay, and you can see a backbone provider connects another to a NAP. So like when you type in google.com and go, it doesn't just like go from here and start traversing directly to Google. It kind of goes up to like a main central, grand central station kind of place. And then your packets go over to another kind of grand central station until it gets to near where the Google server is. Then it starts going down and looking specifically for the server that it's trying to find. So it's pretty cool. Again, IP addresses, I've told you already about this. It says usually in binary form, like we don't have to break that up. But the reason it goes 0 to 255 is because there's 8 bits. And in binary, you use bits to, you can translate binary into decimal value base 10. So for this class, don't sweat it. I normally teach it, but there's no reason for you guys to have to know that. Unless you want to know it, let me know and I'll make a video or something for y'all. But there's always 4 octets between decimals, always 0 to 255, and then there's the public and the private routing. As I mentioned, public addresses are routable on the internet, meaning if you have a public routable address, just like I did right here, the 9999 one right here, I can hit that from anywhere. You at your house right now could ping this. Like people on an airplane, if they have internet, they could ping this, right? You could be anywhere, International Space Station, you can ping this if you have an internet connection, right? So that's what public routable means. Now, private routable, as I've already mentioned, is not routable out on the internet, and that's the way that we're able to have more IP addresses for everybody because of that 192.168 or the 172.16, 172.32 or 10.0, right? Those IP addresses can be reused by other organizations because they won't route to each other, right? So, okay. Network classes. All right, we'll spend just a minute on this. You don't really need to get too wrapped around the axle on this one, but there used to be classful networks, right? This is just a little history lesson. You can see it says classful networks. It used to be like class A was the first octet, and then the 3 octets behind it were IP addressable. And then class B was like the first 2 octets, but it was just, we don't do it anymore since 1993 because it was such a wasteful way of doing, it was such a lazy, wasteful way of doing IP addressing that they came out with CIDR, which is classless IDR. I don't know actually what CIDR stands for, but the C is classless. And the reason that it's great is because you can carve out specific pieces of a network address range that really suit what your organization or your individual situation needs versus just this large block, right? So I've already mentioned that IP addresses are not infinite. We covered that. IPv4 will be replaced by IPv6. So listen, one of the ways that they were going to solve the IP address resource issue was they came out with IPv6. IPv6 is way more complicated than IPv4, And yes, it solves the problem of having more public routable address spaces, but I really haven't seen it adopted wholesale by really any organization. Practitioners and vendors and everything are still using IPv4 for discussing. So just be aware of IPv6, but we're living in an IPv4 world, which is those 4 octets, right? Subnet's a portion of a network that shares the same subnet address. Again, this is where CIDR addressing comes in. When you carve off a piece of a network, you call it a subnet. You guys don't need to know or understand subnetting or how to calculate subnettings. Just know that there is a concept where you can carve off pieces of a network range, IP range, and have that kind of dedicated in a subnet, right? So IPv6, yeah. So with IPv4, there is, 4 octets, right? So there's 32-bit address space. There's 8 bits, 8 bits, 8 bits, 8 bits, right? So 8 times 4 is 32. With IPv6, you got 128 bits. Now, let me just show you, like, this is a IPv6 address right here. Doesn't really roll off the tongue when you say it, right? You could say 192.168.1.204 is my IP, and it's easy to communicate that and convey that. Here, this is not easy to communicate, but this is an IPv6 address, okay? And it supports DHCP, which is getting those IP addresses. URLs. So a URL is basically what I was telling you before, like google.com or amazon.com or www.citadel.edu, right? These are easy to remember for humans, domain names for, basically communicating areas on the internet, right? DNS is that service that I showed you, which translates IP addresses into domain names. And yeah, error message sent by the web server. So if you try to access, if you've ever gotten a 404 error, like resource cannot be found, that's a pretty standard one for people to get. That is an error message being sent back by the web server, an error 404. So there's error and then there's like numbers for all the errors, right? So you can see 400 is a client error, 500 is a server error. So if you've ever gotten, like bad, like the server failed or whatever, you'd get a 500. They're not that common. 200 is the most common, although you probably never see it because 200 means that everything is fine and you're good to go. Occasionally you'll get a 301 redirect where you go to a website and then it'll quickly spin and push you somewhere else. So I don't know if you guys have seen these error messages, but the 404 is really the most common one. So this is an error 404 message from Google when something breaks over at Google. You may have seen this before, but this is what's going on there, okay? Some basic network utilities. ipconfig is how you get this information. So I'm on a Linux-based system, so ifconfig is what I have to use, but ipconfig is for Windows-based computers. It's essentially the same command. So when you do ifconfig, it shows you the interface configuration, which again, network interface card at the MAC layer. So you get all this information. Don't worry too much about it. If you want, you can open a terminal or command prompt on your workstation. You can go to the search bar and type in CMD if you're on a Windows machine, or you can type in terminal if you're on a Linux machine. And you can do ipconfig and ifconfig and see kind of what it brings up. It's not required. It's just if you're interested. Ping is another utility. We've already kind of demonstrated it. I pinged the Google server to show you what's going on there. Traceroute is kind of like ping, except Traceroute shows you every step along the way. So this is actually really interesting considering we've now gone through most of this lecture and talked about how the internet works, where I'm going to communicate with the Google server and it's going to hop across routers until it gets to where it's going. So Traceroute, again, I'm on a Linux-based machine, so the command's traceroute, but if you're on a Windows, it's traceRT. But if we do traceroute, www.google.com, it's going to do that DNS resolution, and then it's going to do the track. So this is it traveling across the internet. So now it just got hooked up somewhere. Oh, there it goes. See? Now, it doesn't really make a lot of sense because it doesn't have domain names and stuff like this, but this is the internet working right here. This is my packet traversing the internet to go to Google's server, right? Okay, so Traceroute allows you to trace the path as you go across the network. Okay. Netstat is like listening services. So you can do Netstat. It's the same on Linux or Windows machines. But if you do Netstat, remember we talked about listening services? You can see all this wonderful information that was brought back here. But basically, this isn't going to make a lot of sense, but let's do this. Netstat. It's all about the network statistics. That's what the command is for. But I want to show you something. I don't have any listening services, which is fine. But here are all established connections. Remember I was telling you about that TCP connection, right? You could see, I don't even know what this is, mailcentral.net, but you could see 192.168.1.144. That's my IP address, right? Looks like I'm doing some IPv6 here as well. And these are all domain names that are already been translated. This is a Amazon web service. You know, I'm not exactly sure what that is, but you get it, right? You see these are all network established connections, and that's what Netstat shows you. And then Nslookup we already did. It basically does the DNS service for you so you can see what the IP address is for a particular domain. Oh, here we go. So I'll just leave this here. You can pause it if you want. If you want to jump in on your particular computer and play around with it, you cannot mess anything up. So don't sweat that. If you're on a Windows machine, it's ipconfig. If you're on a Mac or Linux machine, it's ifconfig. Feel free to take a look. Here's a screenshot of them pinging. I already walked through the demonstration for you. Ipconfig, again, shows your IP address subnet mask. The output on Windows is nicer for ipconfig than Linux. So I'd encourage you to check that out. We already demonstrated what ping is. I've already told you about tracerouting and showed you a bit about it. Here is tracerouting to yahoo.com, just to give you another kind of visual on what it looks like. And Netstat shows you the network status. Okay. Oh, same thing I just showed you. Okay, cool. And Nslookup does DNS resolution. That's fine. And we demonstrated that. Okay, so some other network devices, firewalls. We will do a lab where we have a firewall configured. Firewalls basically, it could be hardware, it could be software. You typically see hardware at larger organizations because it needs to be beefier. But data, traffic comes in. It's like a router, kind of. Comes in, and if it's configured to allow the traffic to continue to pass through, it continues, and if it's not, it blocks it right there. So sometimes, remember earlier I said if you try to ping and it didn't come up, that public IP address that I just randomly made up, it could have been a firewall blocking the traffic from coming in or from going out, right? It's quite possible, or the server just wasn't up there. Proxy servers, they allow you to kind of hide stuff. We talked about that already. So I know this was a lot, okay? And like I said before, if you're feeling overwhelmed about how networks work, don't worry about it, right? As we go through the semester, anytime we encounter stuff, I will reference this lecture. So if I'm like, oh, let's talk about denial of service attacks, which we'll be doing next week. Denial of service attack is where you exhaust. Remember I said those servers are listening and waiting for connections to do the SYNAC handshake? Well, servers only have so much resources. So if I send 100 million SYN packets, right, it'll fill up the queue of all the SYNACs, right? Because the server will be waiting for all of those ACK packets to come back. And that's how you denial of service a web server, right? So when I make a point later on about how you can do malicious stuff or attack certain things, or how defenders configure networks to protect from certain things, I will be referencing this lecture and networking quite a bit. So don't feel overwhelmed and don't feel like you didn't get it. I know it's a lot, but really, really focus on understanding the things I said around the network layer. Where's my OSI stack? Really focus on the things I said about the network layer and about the transport layer, okay? Because those are definitely the most important. And the data link layer a little bit for switches and stuff like that. But for the most part, most cybersecurity activities, both offensive, like people attacking and criminals attacking, and defensive operations, whether you're protecting or you're going through audit logs and trying to piece it all together, it's really at these two layers that most of the work is being done. So that's really where you want to focus. Don't sweat. Really don't worry about the green much. Have a little bit of an idea about this red and orange layer, and then these two in the middle is where we're going to spend most of our time. So again, I know this is a particularly difficult lecture to give asynchronously. I hope you understand. Let me know. This and lecture 1 are part of the first week. You've got a couple discussions. You've got some labs. Let me look at it real quick. Due July 4th, so just a week away, we have chapter 1 quiz, chapter 2 quiz, both open book, both open internet. So make sure you've got an internet connection. You can Google stuff, okay? It'll be covering a lot of the things that I talked about, but this is part of the reason why I think I didn't require the textbook for this particular book, because everything is on the internet, and the slides are available. Do complete this lab, this Nmap lab, where you're going to be scanning a network and seeing some cool stuff. I've made a video for all the labs and posted them so you can watch that. I fully walk through the lab and I explain to you right here what you need to do to complete the lab to prove that you did it. And I say it in the video too. I show you exactly what you need to take a screenshot of in the video, okay? And then obviously introduce yourself. This should take all of like 2 minutes. And then we have discussions every week. So make sure that you comment on the discussion, which I made a video about, talking about the pipeline ransomware event. So watch the video and give me your thoughts on these things, okay? I'm looking forward to this semester. I will be doing all the videos and posting them up, hopefully well in advance. If you got any questions, text me or email me or whatever, and let's continue on. Thank you.